So in this video, today we are going to be deriving the lever rule and using it to explain the vapor to liquid fraction as it changes in a closed container of a binary mixture at a fixed temperature as the pressure is increased and the contents transition from all vapor to all liquid. So I have brought in our plot of bubble pressure and dew pressure. On our x-axis at the bottom, we're going to have our mole fraction of our more volatile component, and on our y-axis, we're going to have pressure and the constant temperature at 393 kelvins. And our blue line is going to represent our bubble pressure, and the red line is going to represent our dew pressure. So if we were to have a mixture of all liquid, it would be somewhere in the region up here with a higher pressure. And if we decrease the pressure below this red line, we would have all liquid down below. All vapor, I'm sorry. I think I said that backwards. So we would have all liquid at the top and all vapor below. So in between those two lines, what we're going to have is a fraction of material in the liquid and vapor phases. So about where this black dot is that I have drawn here, that's going to be at our 0.4 mole ratio, or our 0.4 mole ratio of our more volatile component. And then if we come up, we're going to see that we have 180,000 pascals pressure at that concentration. So we're going to be looking at this transition between those two curves and above and below them. So we're going to start to derive our lever rule. The first thing that we want to remember is how up above here we use the assumption that our total mole fraction of our more volatile component in the feed is equal to the mole fraction of our component in the vapor phase plus our mole fraction of our component in the liquid phase. So that's the idea we're going to begin with. I'm just rewriting that down here for us. And what we want to do is make another mass balance equation. So using this information, we can do the same thing we did up above, where we have our same equation, just multiplying by our mole fraction components. So we'll have T times Zi, where Zi is our mole fraction of the component in the feed. I think I misspoke before. Our T equals V plus L, that's going to be our flow rates going into the feed is equal to the flow rate of our vapor going out plus the flow rate of our liquid going out. And then our Zi is going to be the mole fraction of our component in the feed. And that's going to be equal to our flow rate times the mole fraction in the vapor phase plus our liquid flow rate times the mole fraction in the liquid phase. So because we want this to be as a vapor-liquid ratio, like we have up here, vapor-liquid fraction, what we want to do is get some sort of equation with V over L, which is going to be unitless. So to do that, we can make a substitution of our total flow rate of our feed so we'll have V plus L in substitution for our T. And we can go ahead and distribute that Zi as well. So we'll have V Zi plus L Zi equal to our Vyi plus Lxi. Next, what we want to do is get all of our V's on one side and all our L's on the other side. So we'll have Lzi minus Lxi equal to Vyi minus our Vzi. All right, so we're almost there. We can factor out our flow rate of L, liquid, and our flow rate of our vapor. Okay, so now we can do some division just to get our fraction of our material in the vapor phase over our liquid phase. So we'll have V over L equal to our Zi minus Xi over Yi minus Zi. So this is going to be our lever rule, where we have our mole fraction of our component in the feed minus the mole fraction in the vapor or in the liquid phase for our V, and that's going to be divided by our mole fraction in the vapor phase minus our mole fraction in the feed. So our lever rule is basically saying that the ratio of our vapor to liquid phase that we would obtain from our binary mixture is going to be equivalent to these two distances on our plot here, from the bubble pressure to the center. So from our green dot to the black dot, that pink line there is going to represent our vapor phase, and that's going to be divided by our orange line here, which is going to be the dew pressure minus our total, which is going to give us that orange line there. So why is this the case? Let's look at our equation to justify this. So we are going to have our Z minus X, which is the mole fraction of our component in the feed, which is the center black dot, minus the mole fraction in our liquid phase, which is going to be our green dot over here, our blue line. And we'll have Y minus our Z in the denominator, which is going to be our mole fraction in our vapor phase, which is the red line, or where the purple dot is, minus our mole fraction in the feed, which is again the black dot. So that's what this is describing, and it shows that the lever rule is, it shows that's what the lever rule is about. So what if we were to increase this pressure at our 0.4 moles? The center dot is going to move up and up. So as this center dot goes higher and higher, you can tell that our left line, the pink line, is going to get smaller and smaller, and the right line is going to get longer. So this means that we're going to be getting more liquid phase, which makes sense because if we look at our equation, we have our liquid phase in the denominator, which is going to be our vapor minus the total feed. So that's going to be larger, obviously. So if we were to continue to increase that pressure until we reach our blue line of the bubble pressure, what's going to happen here? So once we reach that bubble pressure curve, so once our black dot reaches this point here, what's going to happen? That is going to be where our last air bubble is before it all condenses into our liquid, because again, we'll have all liquid up here, all vapor down below. So if we were to go the other way, decreasing the pressure, we would have our last drop of liquid before it becomes all vapor as well. So hopefully you can understand why this is called the lever rule, because these lines sort of move like a lever when our pressure changes, or you can kind of think of it like a teeter-totter on a playground. So as our as our vapor is increasing, liquid is decreasing. As liquid increases, vapor decreases. So hopefully you can learn something from this video about the lever rule and from all of our videos about the vapor liquid equilibrium relationship and what those plots would look like, and a little more understanding of its equilibrium in general. So thank you for watching.